Okay, so we'll start off by recapping on what we did yesterday. Basically, we can look at the rate concentration graph of a particular reactant, um, to identify if it's a zero, first, or second order. Okay, so for a zero order, you will see that in the rate concentration graph, it will be a straight horizontal line. Okay, this shows that no matter how much you change the concentration, the rate will stay the same. Okay, so that this is to say that the concentration does not have any effect on the rate of the reaction for that particular reactant only. For first order, it will be a straight line, an increasing straight line that passes through the origin. This is because however much you increase the concentration of your particular reactant, the rate will have the exact same effect. Okay. As for second order, it will be a curve, an increasing curve. This is because whatever effect that you do to the concentration of that particular reactant, the rate will feel the square of that effect. Okay. And then this graph at the bottom is just showing you a combination of your zero, which is the black line, first, which is the blue line, and second order, which is the red line. Okay. The second type of graph that we looked at is the concentration time graph, right? Concentration time graph does not tell you the rate directly. Okay, you have to draw the tangent to find the gradient, which gives you the rate, right? For concentration time graph, the easiest one to spot out is the zero order, because zero order is a straight line. Why is it a decreasing straight line? Because over time, your concentration of your reactants decreases because you keep on using reactants as the reaction proceeds. And the reason why it's a straight line is because at any point of your concentration, your gradient or your rate is the same. Okay, for first and second order, it will be a curve, a decreasing curve. Not easy to spot out unless you do some calculations. Okay, so that's just showing you how to draw the gradient on a curve, whether it's a first order or second order. You need to choose a particular concentration and then you draw a tangent through that point. Okay, and then that brings us to the next concept, which is the half-life. Okay, so just to recall back, the definition of half-life is the time taken. Okay, we want to know the time for the concentration to fall to half of its original value. Okay, for zero order, the half-life would decrease. Now, it's easy to spot a zero order from the concentration time graph because it is the only one that has a decreasing straight line. Okay, first and second order is the one that you need to worry about because it is a curve and it looks similar. Unless you do calculation, then only you should be able to differentiate between the first and the second order. Okay. It says my connection is unstable. Please let me know if you are having problems with audio, my audio or my PowerPoint, okay? Because I've just received a notification that says there's something wrong with my connection. Right, moving on. So talking about the first and second order, the only difference is in a first order, if your reactant is first order, the half-life is constant. Okay, I haven't taught you how to calculate half-life yet, but just remember that point. Okay, for second order, the half-life is increasing. Okay, that's what I thought because my internet is not that stable. Is it just Hamida having this problem? How about the rest of you?
Same with me, miss.
Is it not clear?
Yeah, just now.
Oh, just now. But now it's okay.
Okay.
All right. So just keep updating me, yeah? It keeps
Okay.
lagging out. Okay. Right, so moving on. For the first order of reaction, since the half-life is constant, we can actually come up with a formula for that, okay? T half stands for half-life. We want to know the time taken for the concentration to go down by half, okay? T half is your half-life. ln2 is your natural logarithm, okay? Your yeah, ln, which is the
Miss,
function. Yep.
Miss.
Yes, Fatin.
Apa?
Sorry, what?
Miss,
Yeah.
Miss.
Someone is calling me, but I don't know who. Can you use the chat box? So, right. Going back to this slide. Okay. The formula, there's a formula for a first order reaction only. Okay. The reason for that is because the half-life is constant. T half stands for the half-life. Okay. T half is equals to ln2. ln is the function that you have in your calculator. So you just click on the natural logarithm 2 and divide by k. The k here is the rate constant, okay? And the units for rate constant for a first order reaction is square to the power of -1. How do you know that? You have to work it out, okay? Later on when we do examples, I'll show you how to work out the units for rate constant. Okay, so that's in terms of formula. How do we find the half-life graphically? Okay, so I'm gonna unmute you all. Please have a ruler with you. Do you have a ruler with you?
Yes.
Okay, so what we're going to do with this graph is, now going back to the definition of half-life, okay, the half-life, half-life is the time taken. So we want to measure the time taken when your concentration, which is your y-axis, concentration is halved. Okay, now, so first point, you can start at any point. You can start at 4, you can start at 3, 2, 1. The easiest one is I'll start at 4. Okay, because at 4 my time is 0, right? So my concentration to be half, if I start with 4, half of my concentration would be 2, correct? So I would draw a line a line at that 2 mole per dm cube, and then that the most important thing, the one that I'm interested in, is the time, okay? Because the definition of half-life is the time taken for my concentration to drop by half, okay? So I want you to read off from your graph the value for that first half-life. Okay, we're going to do 3 successive half-lives here. Successive means continuously, okay? From 4 mole per dm cube down to 2 mole per dm cube, and then half of 2 mole per dm cube is 1, okay? So that's the first one. If I keep on doubling my concentration, if I keep on halving my concentration, now I'm starting at 2, I go down to 1, that's half, okay? So I draw again a line, and then I read that time. Now, for my second half-life, the time is not from 0, okay? Because I want to know the time taken when my concentration dropped from 2 to 1. Okay, so this is the section that I'm interested in. So you have to read off the graph for the second half-life. Okay, so that's the second section of your half-life. If we go on further, half of 1 mole per dm cube is 0.5. Of course, we can still go further. Now, that's not a straight line, but when you do it, you should be drawing a straight line, okay? So the time taken for the concentration to drop from 1 to 0.5 is this section of the graph, okay? So now I have 3 successive half-lives. This is what I mean by successive half-lives. It's continuous, okay? From 4 to 2, this is the time. From 2 to 1, this is the time. From 1 to 0.5, this is the half-life, okay? So these are 3 different half-lives, and I want you to measure them, okay? Read them off from the graph, each of these half-lives, okay? Do not start from 0 because that's not the definition of half-life, okay? So I'll give you time to do it. How's it going? Are you okay?
Yes.
Yes.
What sort of half-life are you getting?
17.5.
17.5. Anyone else? Same, 17.5. Is that for the first half-life? How about the second half-life?
16.5.
17.5. And the third half-life?
15.
15? 17? Okay,
16.
so 16, right, it's not far off, okay? Like the first 2, you got it as constant, 17.5, and then only the third one you started to get like 16. So what can you conclude from here? Is this reactant a first order or second order?
Second.
First or second order? Why do you say second? Is your half-life increasing?
No.
No,
First order.
increasing.
First order. I'm hearing first order. The answer is first order. Now, it cannot be a 0 order. Why can it not be a 0 order? How would the graph of a 0 order look like? A straight line, okay? So we can immediately we can immediately reject 0 order. So it's either first order or second order, okay? First order, we said that the half-life is constant, and you got like 17.5, 17.5, 16. Now, the very little difference in value is because of error, okay? Because this was an experiment carried out. So the best answer is first order, because we say the half-life is more or less constant, okay? It cannot be second order because your half-life is not increasing, okay? So we reject second order. Right, let me clear this, okay? On to the next slide, right? So if you see this, okay, from when the concentration drops from 4 to 2, the half-life is 17 minutes. From 2 to 1 is again 17 minutes. and from 1 to 0.5 is again 17 minutes. Now, some of you got 17.5, that is fine, okay? As long as you know that this is first order and you are convinced that this is first order, okay? So please copy this down. This means that whatever the starting concentration of reactant is for the same reaction, the half-life will always be approximately 17 minutes, okay? Now, what do I mean by this? Whatever starting concentration. So for this example, I started from 4 moles per dm cube. Now, you don't necessarily have to start from there. You can start from 3 moles per dm cube, but the half of 3 would be 1.5, and then the half of 1.5, and so on and so forth, okay? You can also start from 2, but that means you go from 2 to 1, 1 to 0.5, as long as you keep on halving the concentration. But the one that we're more interested in is the time, because half-life is the time taken for the concentration to go down by half. Are you all okay?
Yes.
Okay, are you done copying?
Yes.
Yes.
Okay, I'm hearing yeses from the boys.
Yes.
Ladies, are you okay?
Yeah.
Okay. That's Fatin, right?
Yes.
Right. Okay. Again, if you need me to go back to the slides, I can show it to you later on at the end of this session. Please just let me know in the chat box, yeah? Okay, now moving on. And I'll mute you back. So, so far we've looked at finding the orders of a particular reactant from the graph. Okay, we look at the shape of the graph, we calculated half-lives. Now we want to find the orders of reaction based on data, okay, based on numbers that we get from an experiment. First thing is from initial rate data. Okay, now I've already mentioned about initial rate earlier on during this lesson, but just to recap again, the initial rate for a reaction is the rate at the start of the reaction where it is the fastest. It is often obtained by taking the gradient at t equals to 0 of the concentration time graph. Okay, so if you want to know the initial rate, you have to find the rate from a concentration time graph at just after the reaction has started, okay? Just after t equals to 0. Some of you may argue, but at t equals to 0, there's no reaction, the rate is 0. Okay, that's not what the question means. It's just after the start of the reaction, okay? So this is an example to find the initial rate, but you have to use concentration time graph, okay? You find the gradient because the gradient is change in concentration over change in time. Change in y over change in x, which gives you the rate of reaction. Okay. Right, how do we work out the order of reactants ourselves, okay, if we did not have data from the experiment, right? So normally, to work out the rate equation, we do a series of experiments where the initial concentrations of reactants are changed and measure the initial rate each time, okay? So what do I mean by this? For example, yeah, I have a reaction of hydrogen gas reacting with nitrogen monoxide gas to form water, steam, and nitrogen gas. Now, I want to find the orders of this reaction and eventually I want to write down the rate equation. Okay, before I write the rate equation, I need to know the order of my reactants. Okay, so I've got a hydrogen here and a nitrogen monoxide as my reactants, right? In order to find the order of reaction, I need to focus on one reactant at a time. Okay, because order is specifically per one reactant. For example, first order with respect to hydrogen, second order with respect to nitrogen monoxide. So these two reactants will have different orders, okay? If I want to learn, if I want to monitor the order of reaction of my hydrogen, okay, I need to carry out a few experiments that keeps on changing the concentration of hydrogen, okay? Because I want to know what is the effect of changing concentration of hydrogen on its rate. So that is to say, everything else must be the same, but only the concentration of hydrogen I change every time, okay? The concentration of nitrogen monoxide has to be constant, because if I change the concentration of nitrogen monoxide, I won't be able to study the effect of changing concentration of hydrogen on its rate, okay? So I carry out one experiment, a particular concentration of hydrogen, and then I measure the rate of that reaction, okay? And then the second experiment, I change the concentration of hydrogen, maybe increase it by 2, and then I measure the rate. Is the rate increasing by 2? Is the rate increasing at all? Or is the rate increasing by 4? Okay, and then you can carry on further. You change the concentration of hydrogen again, and then you calculate the rate. So for all these different experiments that you carry, you cannot change the concentration of nitrogen monoxide. Because if you're changing, that means you are changing two variables here. You cannot learn about hydrogen on its own. Okay, so if you want to find the order of hydrogen, you only change the concentration of hydrogen at different experiment. It's still the same reaction, but you carry out different experiments. Okay, and then of course you measure the rate. That's the first one if you want to find the order of hydrogen. Now, if you want to find the order of nitrogen monoxides, since that's your second reactant, same thing applies. You change the concentration of nitrogen monoxide only. This time, you keep the concentration of hydrogen constant, okay? Same procedure. You will change the concentration of nitrogen monoxide. You start with one experiment first. Start with a particular concentration of nitrogen monoxide and a particular concentration of hydrogen, okay? And then you measure the rate. That's your first experiment. Second experiment, you change the concentration of nitrogen monoxide. Say you double it, but your hydrogen stays the same. And then you calculate the rate. So from here, you can see the effect of doubling the concentration of your nitrogen monoxide. What is the effect on the rate? Whilst keeping the concentration of hydrogen constant. Okay, I hope that is clear. We'll have a look at the next example. Okay, what's happening here? I think someone is switching on its video. Nat, I think your video is on. Okay, right. Now, looking at example 1. Okay, we have 10 minutes left. Okay, looking at example 1. We have a reaction where my reactants are A, B, and C. okay, to form D and E, right? And then the data given is this table, okay? This table. Now you can see that there are 4 different experiments. It is still using the same reactants. It is still the same reaction, but the only thing, if you notice, is that I'm changing some of the concentrations, okay? Now, in order to calculate the order for a particular reactant, it is easiest to compare 2 experiments where only that reactant is being changed, okay? I'll talk about this in a moment. So just remember, if doubling concentration, rate stays the same, that's 0 order. If doubling concentration, rate doubles, that's first order. If doubling the concentration, rate quadruples, that's second order. Okay, now going back to the statement where it says, compare 2 experiments where only that reactant is being changed. Okay. So what they have done in this experiment is they start with the first experiment, okay? A, B, and C are all your reactants, right? The concentration is given and the rate. Now the rate is the initial rate, okay? So this is what it means. The rate on the last column means the initial rate, okay? So first experiment, they started with 0.1 mole per dm cube of A, 0.5 mole per dm cube of B, and 0.25 mole per dm cube of C, and then the rate is 0.1. Fine, okay? You have an experiment that has a rate of 0.1. In the second experiment, they still use the same reactants but different amounts. Now, what do you notice? They change the concentration of A, correct? From
Yes.
0.1 to 0.2, but they keep the concentration of B and C constant. Why? Because they want to see what is the effect of changing the concentration of A on the rate. Okay, so this is what it means by, if you want to study the order of reaction for A, you only focus on 2 experiments that changes the concentration of A only. Okay, right, so let's have a look at experiment 1 and 2. Okay, if we compare experiment 1 and 2, the concentration goes from 0.1 to 0.2. That is a multiple of 2. Do you agree?
Yes.
The concentration of A is double. Okay, now concentration of B stays the same, concentration of C stays the same. Now what happens to the rate of reaction? It is double as well. Okay, so what can you say about the order with respect to A? 0, first, or second?
First.
0.
First order.
First.
Because you increase by 2, the rate increases by 2. If it's 0, the rate wouldn't change. Okay?
Yes.
Right. So to answer that, okay, as the concentration of A doubles while B and C staying constant, the rate doubles as well. Therefore, the order with respect to reactant A is first order. Okay, so can you please show the working in your notes when you compare experiment 1 and experiment 2? So concentration of A times 2, and then the rate times 2 as well. Are you ready to move on?
Yes.
Yes.
We have 5 minutes left.
Yes.
Okay, right. Next one, we want to study reactant B. Okay, so if I want to study reactant B, I have to compare experiment 1 and 3. Why? Because experiment 1 and 3, if you look at 1 and 3, only the concentration of B is changing. A is 0.1, 0.1. B is 0.5 to 1. C is 0.25 to 0.25. So that means in experiment 1 and 3, only B is changing. Agree? So 0.5 to 0.1 is times 2. Okay, now we want to study the rate. What about the rate? What can you say about the rate? Going from 0.1 to 0.4.
Quadruple.
Times by?
4.
4. So what can you say about the order of reactant B?
Second order.
Second order, that's right. Okay. As the concentration of B doubles, the rate quadruples. Okay. The rate goes up by 4. So you know that this is second order. Please show the working as I have done it here, so that you can see that between experiment 1 and 3, the B increases, and then between experiment, the rate also increases by 4. Okay, moving on to the last one, because we are running out of time. Last one is I want to study the reactant C. Okay, in order to study the reactant C, I hope you can see that between experiment 1 and 4, only C is changing. A stays the same, B stays the same, C is doubled, times by 2. What can you say about the rate?
It's the same.
It's the same.
Unchanged.
Okay, unchanged, that's right. So what can you say about the order with respect to C?
Zero order.
Zero order, that's right. Okay, so for reactant C, you can write it, the rate is unchanged. So hard to spell. Unchanged. Okay. Right. So to conclude, okay, your reactant A is first order, reactant B is second order, and reactant C, sorry about that, it should be C, okay? Reactant C is zero order. Now, how can you write the rate equation? Rate is equals to K, rate constant, times A to the power of 1, times by concentration of B to the power of 2, and concentration of C to the power of 0. C to the power of 0 is just nothing, 1, okay? That's why you don't see reactant C in this rate equation, okay? So I think I will get disconnected at any point now, right? So please make sure you write down the rate equation. Okay, I will WhatsApp you, I will text you on your homework, because there is some questions that I want you to do from exercise 8.1. Okay, is everyone okay?
Okay.
Yes.
Okay, right, thank you everyone. Assalamualaikum.
Waalaikumsalam.
Waalaikumsalam. Thank you, Miss.
Okay, you're welcome. You're welcome. Bye.
Bye.